Hey guys, Mr. Mackey here, and welcome to the final episode of Sequences Week. Now, yesterday I introduced you to quadratic sequences for our 50th episode. Wow, has it really been that many? Doesn't feel it. 500 episodes feels. But anyway, so I gave you this challenge yesterday where I gave you 3 sequences and I want you to find which 2 were quadratic, and for the ones that were quadratic, find the 6th term of that sequence. So, let's go through it. So the first one, we have a sequence here. How can we tell if it's quadratic? Well, remember, the difference between the differences must be the same. So the difference between 2 and 5 is 3, 5 and 11, 6, 11 and 20, 9, 20 and 32, 12. And the difference between those differences are 3. So this is a quadratic sequence. So how do we find the next term of it? Well, if the differences are going up by 3 every time, then for the next one, there'll be a difference of 15, because 12 and 3 gets us 15. So the 6th term of this sequence is 47. Now, what about this sequence? Is this linear? Is this quadratic? So what you do is you check. There's a difference of 5, difference of 5, difference of 5, difference of 5. The differences are the same. There's another sequence that this applies to, and these are linear sequences. And because this sequence is linear, it can't be quadratic. So by process of elimination, this is a quadratic sequence. But what else can tell us this is quadratic? Well, because the highest indice there is to the power of 2. And that's another way to tell that it's quadratic. So let's find the 6th term. Well, it's pretty simple. All you've got to do is you substitute n for 6. So do 2 times 6 squared minus 6 minus 5. 6 squared is 36. 2 times 36 is 72. 72 minus 6 is 66. Minus 5. So the overall answer, the 6th term for this one, is 61. So now we know how to generate and find terms of quadratic sequences. Today, the creme of the creme, I am going to show you how to find the nth term of a quadratic sequence. Let's do one now. Now, to find the nth term of a quadratic sequence, it's the hardest to find out of all the others we've done. So, there's a step-by-step method. So I have a quadratic sequence. 4, 7, 12, 19, 28. I know they're the same. I know it's a quadratic sequence because the difference between 4 and 7 is 3, 7 and 12, 5, 12 and 19, 7, 19 and 28, 9, and the difference between those differences are all 2. Now that is step 1. Find the difference between those differences, which is 2. So that's step 1. Step 2, you halve that difference. So if the difference between those differences is 2, you halve 2, and what do you get? You get 1. So the first part of this quadratic sequence is 1n squared. 1n squared is the same as n squared though, so we can leave it like that. So that's the first part. We found out what goes in front of our n squared, which is 1. But when we write down the n squared sequence, I'll write it up above. So n squared, so the first one is 1, then 4, then 9, then 16, and 25. Because you know it's the first term squared, second term squared, third term squared. You'll notice they don't match. So the question is, how can we make them match? Well, how do we get from here to here? You add 3. Here to here. You add 3. Here to here. Add 3. There to there. Add 3. And there to there. You add 3. So the nth term of this quadratic sequence is just n squared plus 3. And that's how you find the nth term. It's a complicated step-by-step method, but once you get the hang of it and you don't make the misconceptions that you can sometimes do, forgetting to divide that, forgetting that you have to add 3 that side and don't have to reverse the process, it becomes clockwork. Let's try another one. So I have this sequence. -3, 3, 13, 27, 45. Now let's find the nth term. So firstly, let's find out what goes in front of our n squared. So let's find the difference between them. -3 and 3 is 6. 3 and 13 is 10. 13, 27 is 14. 27, 45 is 18. Now the difference between those differences are 4, 4, 4. Now what do? We halve the difference between those differences. So we halve 4. So the nth term starts with 2n squared. It starts with that. Now I'm going to write that 2n squared across here. So let's do it. So first term, if it's the first term, we do 2 times 1 squared. That just gets us 2. The second term, 2 times 2 squared. That gets us 8. 2 times 3 squared gets you 18. 2 times 4 squared, 32. 2 times 5 squared, 50. Now obviously they don't match, so how do we get them to match? So how do we go from 2 to -3? U minus 5. Minus 5, minus 5, minus 5, minus 5. So the nth term of this sequence is 2n squared minus 5. And that's how you do it. Now let's try it for this sequence. I have 4, 8, 14, 22 and 32. Let's find the difference between those differences first. So the difference between 4 and 8. 4, 6, 8, 10. The difference between those, 2, 2, 2. So we now know we halve that. So the first part is n squared. Sorted. Now let's write that n squared on top. So I'm going to get my pen. I'm going to write 1, 4, 9, 16, 25. Now, how do we make them match? So let's figure it out. You add 3. You add 4. You add 5. You add 6. You add 7. What? That's a bit weird. We're adding on different numbers every time. That's bizarre. Ah, that can happen though. Sometimes you might end up with differences that aren't the same, so you have to do more to make it work. Now I'm just going to write over here those set of numbers. So the difference between 1 and 4 is 3, 4 and 8, 9 and 14, 16 and 22, and 25 and 32. Sorry, I've run out of space. Can you notice something about this sequence? It's linear. They're going up by the same number every time. So sometimes you might have to add a linear sequence to your quadratic sequence. So what is the difference between 3 and 4? It's 1, 1, 1, 1. So the first part of the next part of the sequence is n squared plus n. Now the final part of this is how do we turn the 1 times table into that? You add 2 every time. So the actual answer, the nth term, is n squared, because we're doing it because it's quadratic, plus n plus 2, because the n plus 2 is the linear sequence that we've generated by the difference of our n squared and our actual quadratic sequence that we're finding. So the overall nth term is just n squared plus the linear sequence of n plus 2. This is the hardest question you'll get. As long as you can understand how to do this, you'll be absolutely fine. Now, obviously, because this is the last week of sequences week, last day of it, we're going to do the challenge right now. I'll see you in a minute. Now, I have 3 sequences on here. All of them are different types. One of them is linear, one of them's quadratic, one of them's geometric. Now I want you to find for me which one's which and the nth term for each. I'm going to go over it in 5 seconds, so pause the video now if you want some time to work on it. 4, 3, 2, 1, let's do this. So, let's do the one that we think is linear first. So, linear, it means it increases or decreases by adding or subtracting the same number. That is not the same number, that's multiplying, it must be the middle one. So, what is this sequence going up or down by? It's going down by -5, so it's going down by 5 every time. That's the same as the -5 times tables, or -5n. How do we make it the same? We plus 85 every time. So the nth term of this sequence is -5n plus 85. I'm not doing much working out for this because obviously I don't want to take too long on this, because we've done a lot of linear sequences, a lot of geometric, but not much quadratic. So you should know how to do this by now. So the nth term for this is -5n plus 85. But if you got 85 minus 5n, that's also okay if you got them the other way round. Now for the geometric sequences, because that's being multiplied every time, all you've got to do is you've got to find the first term, which is 1. What we're multiplying by, which is 2, to the power of n minus 1. So that's the nth term of this sequence. 1 times 2 to the power of n minus 1. If you put just 2 to the power of n minus 1, because anything times by 1 is just that, that's also fine. But if you put 1 times 2 to the power of n minus 1, because that's how I've laid it out in the past, that's absolutely fine. So this one must be quadratic. So let's work it out. The difference between the differences, that's 2, 4, 6, 8. The difference between the differences are all 2. So that means it's n squared. So let's write n squared above. 1, 4, 9, 16, 25. The difference between those differences are, I'll write them next to each other, 0, 1, 2, -1, -2, -3, and -4. So we have to add a linear sequence to it. Now, which linear sequence goes down by 1 every time? So I'm just going to write the -1 times table now above. So -1, -2, -3, -4, -5. And that was the sequence that we were worried about. -1, -2, -3, -4. How do I make them match? You add 1 every time. So the nth term of this quadratic sequence is n squared minus n plus 1. I'm sorry it was a little bit rushed. It's because I don't want this video to be too long. And also we have done a lot of sequences, and I also need to let you guys know something important. There won't be a video tomorrow. The reason why is because tomorrow is my birthday. And I want to spend a little time with my mum. Even though we spent about 7 weeks together already under this lockdown, we want to take a break from work and play a few board games, watch a couple of films, just have a bit of fun and celebrate my birthday. So I won't be doing a video tomorrow. So I will be back on Tuesday, the 12th of May. Okay, I'm looking forward to that, and we're going to be focusing on graphs. We're going to be doing graphing week on the 12th. We'll do 6 episodes. What will I focus on? I'll give you a clue. You need to understand linear sequences for graphing week. So spend a bit of time on that. If you want me to go over sequences again, comment below on this video. And don't forget to like, share and subscribe this channel, because the most important thing is we need to keep our children learning. Take care, guys. Hope you enjoyed sequences week. I know I did. And I know they were difficult, but we managed to get through it. Have a good day, guys, and I'll see you when I turn 23.